For a lot of things in chemistry, we think of things happening in the forward direction, but the reality is almost everything is an equilibrium. All processes are equilibrium processes. All reactions are equilibria. And so if we think about the transition from a liquid to a vapor or a liquid to a gas, that is an equilibrium process, and we can indicate it with this double-headed arrow. We'll spend a lot of time in Chem 2 talking about reactions that have this double-headed arrow. This is the equilibrium arrow. And liquid and vapor are in equilibrium with each other, and it's a dynamic equilibrium in that even if it appears that the amount of liquid and the amount of vapor isn't changing, at equilibrium there's still some liquid going into the vapor phase and some vapor going into the liquid phase. It's just that these two processes are happening at the same rate so that it appears that nothing is changing. There is a principle in chemistry known as Le Chatelier's principle. We'll spend a lot more time with it a little later on, but essentially it says that if you have a dynamic equilibrium and you stress this equilibrium, if you apply a stress to it, then the equilibrium shifts. Now the liquid to vapor phase transition, which is what we have drawn here, is an endothermic process, meaning that heat is required to be input in order to get a liquid to go to the vapor stage. So this is an endothermic process, and we learned in thermodynamics that we can write heat as actually part of the process. If you raise the temperature on a liquid system in equilibrium with its vapor, the reaction, this dynamic equilibrium, will actually shift to the right, producing more vapor. And that's Le Chatelier's principle. Raising the temperature means that you have more vapor, more of the substance in the vapor phase, which means your vapor pressure is higher. At higher temperatures, you have a higher vapor pressure. All right. In terms of intermolecular forces, which is something that we've talked about in this module, if I have a liquid that has stronger intermolecular forces, if I have higher or stronger intermolecular forces, those forces are going to tend to keep the particles very close together, and that gives rise to a lower vapor pressure of the substance. So if I'm comparing similar substances, I can put them in order of relative vapor pressures, as long as I'm talking about the same temperature, by comparing their intermolecular forces in a similar fashion to what we did to compare boiling points. But for all substances, regardless of how they compare to other substances, a higher temperature means you're going to have a higher vapor pressure. This is not a linear relationship. This is not a linear relationship, but there is an equation that relates temperature and vapor pressure of a substance, which is just the pressure of the gas phase above the substance, and that equation is called the Clausius-Clapeyron equation. The Clausius-Clapeyron equation is written, it was derived using thermodynamics, and it looks like this. The Clausius-Clapeyron has the natural log of P, and this is the vapor pressure. Remember that vapor pressure is just a pressure. Ln is a natural logarithm. You've got a button on your calculator for this. The delta H of vaporization, this is the enthalpy of vaporization for the substance, is the amount of energy required to cause a liquid to become vapor, to vaporize. It's usually written as a per mole quantity, or sometimes we find it per gram, but most commonly per mole. R is our ideal gas constant, but it is written with energy units, 8.314. The units are joules per Kelvin per mole. This is identical to the gas constant that we saw in the chapter with gases, the 0.0821. It's just that the units have been converted to energy units. T is the temperature, and the temperature has to be in Kelvin in order for this equation to work, and then C is a constant. Essentially, this was derived looking at the laws of thermodynamics, and we will talk more about thermodynamics in a later chapter. But this equation, the Clausius-Clapeyron equation that we see here, is very, very useful for determining enthalpy of vaporization. All right, let me clean this up a little bit, and we see our equation. This is the equation, this is the Clausius-Clapeyron equation, and it is in the form of the equation for an equation for a line. Recall that an equation for a line is y equals mx plus b, where y is your y-axis, x is your x-axis, m is your slope, and b is your y-intercept. So a plot, an experimental plot, putting the natural log of p on the y-axis, this would be the vapor pressure, and 1 over T, the temperature in Kelvin, on the x-axis, means that our slope, there's our x-axis, 1 divided by T, there's our y-axis, natural log of P. That means the slope of this line, and it will be a negatively sloping line, is negative delta H of vaporization over R, that constant, that ideal gas constant in the energy units. So in the laboratory, I can measure vapor pressure of a substance. I need a way to monitor it. We're actually doing an experiment over this semester. If I monitor the vapor pressure of a substance as a function of its temperature and I make this plot, I can actually calculate the enthalpy of vaporization for the substance.